Welcome to Conceptual Physics. This is Chapter 7. We are now going to be working with momentum. Momentum. You may have heard the concept momentum before, but we're going to get into the real physics meaning of momentum. So this is Chapter 7. All right, momentum. This is inertia in motion. Momentum is inertia in motion. Basically, the mass of the object multiplied by its velocity. So we're just looking at mass and velocity right now. We're going to bring some other variables in a little bit, but mass and velocity is basically what makes up momentum. Momentum equals mass times velocity. So it's very easy to find. Three-variable equation. So a large truck has more momentum than a small car if they're going the same speed. But a small car going very fast can have a greater momentum than a large truck going very slow. You see the difference here? It's going to be the combination of mass and velocity. So you can have a very small object that doesn't have a lot of mass have a lot of momentum if it has a lot of velocity. All right, if the momentum of an object changes, either the mass or velocity, or sometimes both change. Mass usually stays the same, so it's usually the velocity is what changes. And if velocity changes, acceleration occurs. We'll have to go way back to Chapter 2 when we talked about acceleration. Remember, if velocity changes, that's basically the definition of acceleration. So when your velocity changes, you have to accelerate. So what causes acceleration? We just covered this in the last chapter, force. So you see how all the chapters that we're working on, acceleration, forces, velocities, this is all still coming back together to deal with momentum. The greater the force acting on the object, the greater the change in velocity, hence a greater change in momentum. So the bigger swing of velocity, the bigger change in momentum you will have. How long the force acts on the object is very, very important. A brief force will cause a very small change in momentum. The same force over an exerted period of time will give you a greater change in momentum. So both force and time are also important in changing momentum. So force and time, mass and velocity, these are all interlinked together. So we said momentum was mass times velocity, and force times time is something that we call impulse. Impulse, this is force times the time interval. We use the capital I for impulse equals force times time. And the great thing about this is that impulse is equal to momentum. Impulse equals momentum. So impulse equals change in momentum. So you can also write this as Ft equals mv. Force times time equals mass times velocity. And you'll be working some problems like this whenever we get to the workbook stuff. You're getting those questions today. So impulse is force times time, momentum is mass times velocity, and they are equal to one another. This is a key concept you kind of need to get. It's basically impulse equals momentum. And impulse is change in momentum. All right. Increasing momentum. When hitting a baseball or a golf ball or kicking a ball, you want to hit it with a large force for a long time. So you want an impact force to be great. That's why you have a follow-through. If you've played any kind of sport where you've swung a bat or swung a club or something like that, your coach always tells you to follow through and swing all the way through the ball because you're going to have a greater change in momentum. You're going to impart a bigger impulse onto the ball by doing that. To decrease momentum. To stop a car, here's a little scenario for you. To stop a car, you can either hit a concrete wall or a haystack. Which one would you hit? Which one do you hot? There's another misspelling for you. Why would you hit which one? Concrete wall or haystack? I'm probably going to pick the haystack, but I don't know why. You will be decreased by the same impulse whichever you choose. So think of it this way. The same force and time, the sum of force and time will be the same no matter which one you choose. The same impulse does not mean the same amount of force or the same amount of time. It means the same product of the force and time. So when you hit something and you want to decrease the momentum, do you want to hit with a large force and a small time, or a large time and a small force? By hitting the haystack, the impact time, the time during which your momentum is brought to zero, is extended. So you want to have a long period of time, and the haystack is going to do that. If you hit the brick wall or the concrete wall, you're going to have a very large force in a very small amount of time. If you hit the haystack, it's going to take a longer time for you to stop, so the force will be less. A longer impact time decreases the force of the impact and decreases the deceleration. So, key concept to this is the ratio, or basically the relationship between force and time. If you want to have a large increase in momentum, you want a large force in a very small time. If you want a decrease momentum, you want a large time and a small force. All right, when you catch a baseball with your bare hand, do you just catch it, or do you give a little when you catch it? Same thing when somebody kicks you a ball. Do you just put your foot there and let the ball hit it, or do you back your foot up a little bit as you receive the ball? When you jump off of something, do you land stiff-legged, or do you bend at the knees when you land? How hard would that be? So let's say you stand on the table and you jump off and you lock your legs and land. Well, I would probably shatter my kneecaps if I did that. Everybody hits and they bend their knees. Wrestlers roll when they fall. They go to feet, knees, thighs, hips, arms, all to reduce the impact time, thus reducing the force and deceleration time. Basically, you're increasing the time with all of these that it takes to stop the ball. Longer time, less force. All right, now we're going to talk about bouncing. A lot of people say you're just going to have things bounce off of something else. Let's talk a little bit about this. Say that you're walking down the street, and if a flower pot falls on your head, you may be in trouble. If it bounces, you might be in serious trouble. Why is that? Because impulses are greater when objects bounce, and here is why. The impulse required to bring an object to a stop and then back up again is greater than just stopping it. Think about that. Say the pot falls and just breaks on your head. Well, then the force is just going straight into your head and then stopping, because it's broken. Suppose you catch the pot and then you throw it back up again. You decelerate the pot, then you provide the impulse to throw it back up again. If the pot hits your head and bounces, then your head provides the impulse for the bounce. So instead of it just falling and breaking on your head, first it's going to hit your head is going to decelerate it to zero, and there's one basically collision with your head, but then your head has to provide the bounce to have it come off your head, so that's like getting hit twice. All right, now we're getting into conservation of momentum. Conservation of momentum. What does Newton's second law say? That was our force equals mass times acceleration. To accelerate an object, a net force must be applied. So for momentum, to change the momentum of an object, you exert an impulse on that object. Now remember, we said impulse is equal to momentum. You apply a force times time on an object, the velocity will change, moving the mass. Either the force or impulse has to come from outside the object. Pushing on the dashboard of your car does not change the momentum of the car. That would be an internal force. If no external force or impulse is applied, then there can be no change in the momentum. So you're sitting there in your car and you're trying to get it to go faster and you're pushing on the dashboard. That doesn't make your car go faster. Somebody behind your car pushing it, that's an external force. That could make it go faster. All right, again, like just about everything we worked with this year, remember momentum is a vector. Vectors have magnitude and direction. Magnitude and direction. So momentum can be canceled out or brought into equilibrium. Remember we did balance torques in the last section? Now we're going to be balancing momentums, basically. Think of a cannonball system. Think of a cannon, and it's sitting there with a cannonball. Well, you light the fuse and the cannon fires, correct? Well, the cannonball shoots out of the cannon. What does the cannon do? Does it shoot far back the other way? No, it moves just a little bit back the other way. Well, why does the cannon not go as far as the cannonball? Well, that's because the cannon has much more mass than the cannonball. It was the same explosion that moved both of them. It was the same amount of force that was applied to them from the explosion of the gunpowder, but that explosion shot the cannonball very far because it has way less mass than the cannon. But if you look at the whole system in general, it's going to equal out. The cannon fires the cannonball. The force on the cannonball is equal to the force pushing back on the cannon, so the net force acting on this is zero. And if your net force is zero, what's your acceleration? Zero. If no net force or net impulse acts on a system, the momentum of the system cannot change. Basically, it balances out. You have momentum on one side, momentum on the other side. All right. We're talked about conserved, and we're going to get more into conserved when we get to the energy after spring break. Conserved is when momentum or any other quantity does not change. So we're talking about conservation of momentum. Whatever momentum you start with will equal the momentum you end with. And they might not be in the same ratios. You might have more velocity on one side, or you might have more mass on the other side, or something like that to balance it out, but it'll always balance. Law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. So I'm going to say that again. The absence of an external force, the momentum of a system remains unchanged. This works with collisions. The net momentum before your collision will equal the net momentum after your collision. And we're going to talk about collisions, and you're going to work problems with collisions. We're going to start with elastic and inelastic collisions. The key that they always ask about on the tax test is like billiard balls when you're playing pool. If one ball hits another ball, what happens to the other ball? This is a type of momentum, and we'll talk about that during problems. All right, the first type of collision I want to talk about is an elastic collision. This is when objects collide without being permanently deformed and without generating heat. This is like your billiard balls hitting each other. They hit each other, they bounce off, they don't deform, they don't get cracked or anything, and they do not generate any heat. That is the key thing with elastic collisions. They hit and bounce off one another. The other type is an inelastic collisions. This is when objects collide and become tangled or crumpled together and do generate heat. Heat is a type of energy, and we're going to talk more about that when we get to the energy section. So elastic is when they hit and bounce off one another. Inelastic is when they hit and crumple together and deform each other and travel as basically one object afterwards. And you'll see that whenever, and they do generate heat. And we'll see these when we work the problems. So I think this is the last of the notes, and we will also do workbook for this. Oh, I was wrong. One more. Friction. I forgot to talk about friction. Friction at the point of impact is negligible, so is not taken into account. We're basically going to neglect friction for most of the stuff that we do from here on out. Friction produces an impulse to decrease momentum after a collision, but we're mostly just going to be talking about the collision, not what happens after a collision. So we're basically not going to take friction into account.